We're going to end by talking about how we can look for certain properties in the digraph and matrix representations of a relation to determine what properties it has or doesn't have. Let's start by using the digraph representation for this example R. I'm going to make my vertices A, B, C, and D, and I'm going to draw directed edges if there is a ordered pair connecting those two in that order. So A comma A, I'm going to draw a loop. A comma B is going to be a directed edge from A to B. And B comma A is going to be a directed edge from B to A, like that. I have C comma C, that's going to be a loop at C, a directed loop. B comma C would be an edge from B to C. DC is this directed edge. And finally, AC is the edge that goes from A to C in that order. Now let's think about reflexive, irreflexive, symmetric, antisymmetric, and transitive. Okay, so if R were reflexive, what would we need in this digraph that we don't have? If you said we need loops at every vertex, you are correct. So if we were going to make this reflexive, we would need loops here and here. We would need to add BB and DD. So because we're missing those, it's not reflexive. Now the question is it irreflexive? Well, irreflexive means we have no such ordered pairs of the form AA or CC, for example. So it's not irreflexive either. We would need to remove these loops if we're going to make it irreflexive. But that's not going to happen, so it's not irreflexive either. What about symmetric? So symmetric would mean, let's see, we have AB and BA. So we have, if AB is in the relation, then BA is in the relation. That's definitely true here, but is that true for every possible pair that you can consider here? For example, this one. If BC is in the relation, then we would expect CB to also be in the relation. What does that look like in the digraph? So hopefully you're thinking of things like, well, if I have an edge going there and coming back for every possible pair of edges that have any kind of connection between them, then that would make it symmetric. In other words, what would we have to add to make the current relation symmetric? I'd have to add an edge going from C to B, which means I'd need the ordered pair CB, and then because I have D to C, I need C to D, so I need the ordered pair CD. And then also, because I have A to C, I would need C to A, so I'd need to add quite a bit more to R in order to make it symmetric. So that's what's missing. That's what's preventing this relation from being symmetric. What about antisymmetric? Antisymmetric says if AB and BA are in the relation, then A equals B. Well, from this diagram, we can conclude that A is not equal to B. They're viewed as distinct elements. So this alone tells us that the relation is not antisymmetric. But let's say we removed something. Let's say we took away this edge. In other words, we took away the ordered pair BA. If we did that, would this now be antisymmetric? So what that is for any distinct pair of elements of A, you have that the ordered pair AB or the ordered pair BA or neither is in the relation, and that's definitely the case. So notice what it looks like when it's antisymmetric. You go one place, you don't come back. Symmetric, if you go somewhere, then you have to come back. So I can see how one might think that they're opposites of each other, but they're not exactly opposites. All right. Last but not least is transitive. So transitive, we have, if I go from A to B and B to C, I should be able to go straight from A to C. And that's definitely true for these ordered pairs. Oops, I forgot to bring back my ordered pair that I erased. What was it now? It was B comma A, I believe. So let's put that back here. All right, so transitive would mean for every possible situation where this is meaningful, AB and BC in the relation implies AC is in the relation. That's definitely true here, but think about this. What if we do BA and AC? If we consider BA and AC, is it true that BC is in the relation? Oh, yeah, actually. Let's see, what else? What about from D to C? Well, going from D to C, C doesn't actually go anywhere except to itself, so that's gonna not cause a problem. So think for a moment, is this transitive? Well, it turns out, yes, this relation is transitive. Now let's look at these criteria to look for in a digraph and review what we just talked about. Looking at the digraph representation of a relation, that relation will be reflexive if there's a loop at every vertex of G. Remember, we added in some loops to make it reflexive temporarily just for exploration. Irreflexive if there's no loops at all. Remember when we erased the loops. Symmetric if every pair of vertices is connected by none or by exactly two directed lines in opposite directions. So for example, A and D are not connected by edges at all, so that doesn't violate the definition of symmetric. It just means we don't need to really consider them. They're not getting in the way. But because we have AC in the relation, we need to have CA in the relation. That's what's preventing this relation from being symmetric. And then antisymmetric if every pair of vertices is connected by none or by exactly one directed line. So because we have, an edge, a way there and back between A and B, that's what prevents it from being antisymmetric. And then transitive, let's look at this one. It's transitive if for every unidirectional path joining three vertices A, B, and C in that order, there is also a directed line joining A to C. Okay, unidirectional path. That's just a fancy way of saying I go from A to B, B to C. So I have a unidirectional path. It's going in one direction. It's going from A to C through B, and I have the edge that connects A to C directly. So that's true here. If I start at B, there's a unidirectional path from B to C through A, but there's also a directed line joining B and C. Remember, the A, B, and C, when we're talking abstractly, talking in general, those are just placeholders. We have to check it for every single situation that is relevant. So yes, this is transitive. So what did we say? We said it's not reflexive, it's not irreflexive, it's not symmetric, even though it has parts that make it seem like it could be. It's not anti-symmetric, even though it has parts that make it seem like it could be. And it is transitive. So the only property of these that it has is that it's transitive. What about the matrix of a relation? Let's take a look at the matrix. Okay, so the matrix, remember, I'm going to label each row and column with the elements of the set A, and we put a 1 if an ordered pair is in that set. So A comma A, is that in the set, in the relation? Yes, it is. We put a 1. A comma B is in the relation, so we'll put a 1. A comma C, there it is, put a 1. A comma D, that's nowhere to be found, so we're going to put a 0 here. B comma A, there it is, put a 1. B comma B, that's missing, so we put a 0. B comma C, yeah, there it is. And then B comma D, B comma D, I can't find it here, so put a 0 there. If we continue in this way, filling in what's there, first of all, we should notice there should be a total of 7 ones, no more, no less, in this matrix when we're done. That's a good way to check if you did this right. So if I continue filling in my zeros and ones, I should have 7 ones. So let's see, 1, 2, 3, 4, 5, 6, 7. Okay, looks like I did this right. Now, what are we looking for in the matrix when we're talking about reflexive, irreflexive, symmetric, anti-symmetric, and transitive? Well, notice the loops, or the ordered pairs of the form A comma A, will all be on the diagonal. Okay, so for reflexive and irreflexive, I'm looking at the diagonal. If these were all ones, I would say the relation is reflexive. If they were all zeros, I would say the relation is irreflexive. But since we have a mixture of zeros and ones, that's why the relation is neither reflexive nor irreflexive. What about symmetric? B comma A and A comma B. Let's see. So if AB is in the relation, then BA is in the relation. Okay, that's true here. But what about BC? So BC is in the relation. Is CB in the relation? No. So notice what's happening across the diagonal. Okay, across the diagonal, they need to be identical. So in other words, if you exchanged rows with columns, you would get exactly the same matrix. That's how you know that the relation is symmetric based on the matrix. Okay. And let's see, there's anti-symmetric. Now for anti-symmetric, remember the thing that got in the way of anti-symmetric was having the BA, right? When we looked at the digraph representation over here, if we removed the BA, then it would actually become anti-symmetric. So we're going to temporarily pretend that this is a 0 here. What do we notice? We have, across the diagonal, we have 0 and 1, 0 and 1. Here we have 0 and 0. Here we have 0 and 1, 0 and 0. Here we have 1 and 0. In other words, we're never going to have a 1, 1 if we're going to have anti-symmetric. Okay, so when I temporarily thought of this as a 0 instead of a 1, I was showing what anti-symmetric would look like in a matrix. But because we have a situation where there's a 1 and a 1, that prevents the matrix from being from representing an anti-symmetric relation. Transitive, we have to kind of think of a little bit more. Transitive has to do with paths linking with each other and a direct path from the beginning to the end. A good way to do that with a matrix is if I took this matrix and multiplied it with itself, in other words, if I squared the matrix, by the way, that was an extremely quick review of how to multiply matrices, but back to how that applies to transitivity. If the square of the matrix, if an entry in the square of the matrix implies, being positive implies that an entry in the original matrix is 0, then that will be the situation where we have transitive. So let's check that. 2 is greater than 0, 1 is greater than 0, 1 is greater than 0, so is 1. We just ignore all the zeros in the square matrix and go to this one here. 1 is greater than 0 implies 1 is greater than 0. That's true. And then there's 1 is greater than 0, but 0 is not greater than 0. Oh, yeah, but it says whenever I is not equal to j. I not equal to j basically means off the diagonal. So ignoring the diagonal, in every case where the square of the matrix has a non-zero entry, the original has a non-zero entry also. So this verifies our observation earlier that this relation is transitive. Okay. So to summarize, this section was talking completely about relations from a set to itself. And then we had these 5 properties that we were looking for in the relation. Here's the review of those definitions. And we had a couple of alternate ways to think of anti-symmetry, because that one tends to be kind of a lot to think about. And then if you can relate two elements that are related via a third element, that's transitivity. That's another way to think about transitivity.